Welcome everyone to my presentation on computing the sampling performance of event-triggered control. I'm Gabriel Gleizer, a PhD candidate at TU Delft under the supervision of Malan Matho. Simple data and networked control are the prevalent techniques of implementation of control nowadays. Many reasons for their success because of needing of increasingly complex systems or new applications, because they allow to save a lot of hardware footprint, and engineering costs. And because we can do that, because of smarter sensors, cheap hardware, and reliable control targeted networks. And in this context, while the prevalent implementation in networks is through periodic sampling of states and outputs, a paradigm shift happened 15, 20 years ago with the advent of event-triggered control. Event-triggered control is a sampling strategy for control that instead of doing periodic sampling, we have a condition mechanism, a condition checking mechanism that checks whether the state is violating some pre-designed condition. And when it does, it sends the message to the controller, which is in the digital world. And then the controller will naturally compute its input, and then this input will be updated to the plans. Main objective of event-triggered control is reducing communications. And reducing communications can allow that we move from short platoons of cars to larger interconnected cars and larger portions of the railway cooperatively interconnected. But especially when you have wireless modes, and in this context of energy harvesting, reducing communications and therefore reducing the energy consumption through radio can make the difference between having to eventually replace batteries of modes or having a fully energetically sustainable control loop. So ETC is very interesting, but how significant are ETC savings? Can we actually prove that the savings are significant? Well, this has actually been the elephant in the room for my PhD since I started this 3 years ago working with ETC. And we decided to compute the minimum average intersample time, which would be a measure of the worst case average resource utilization of ETC. And most papers that do ETC actually compute these numbers, but only through numerical simulations. So the results are normally the formal results, normally targeted to stability and control performance. But when it comes down to the average sample time or the average resource utilization, there are no formal results at all, or very, very conservative estimates. Even the qualitative analysis of ETC traffic is just very recent and quite limited. There's this very interesting work from Postoyan, Sanfelice, and Hamos in 2019 CDC, where they analyzed planar linear event-triggered control systems with small triggering parameters. So if qualitative analysis is quite limited, quantitative analysis or computing these metrics, they were absent. And for this reason, we decided to tackle this problem. And so our aim was to devise a method to compute the average sampling time of event-triggered control systems. Now, of course, we couldn't do it for all event-triggered control. We decided to narrow the scope to what would be hopefully the simplest case. This would be periodic event-triggered control of linear systems with static state feedback and quadratic static triggering conditions. So let me explain that. PETC, or periodic event-triggered control, is a more practical version of ETC, where the condition checking mechanism is done periodically. So you have the triggering condition checked every H time units. Now, the quadratic triggering conditions are functions of the current state and the last sampled state, and this form here encompasses most of the commonly used triggering conditions in the literature. Well, using PTC facilitates building traffic models. Traffic models are models of this closed loop system, but with the output being the intersample time. And why do they facilitate? It's because the inter-event times are now in this discrete set, H2, H3, H, so on and so forth. And if we impose a maximum inter-event time, we have now a finite collection of outputs. Now, imposing a maximum inter-event time is not very artificial requirement at all. Normally, for open loop unstable systems, maximum inter-event time will naturally happen. And even if it doesn't happen, it's natural that we want a heartbeat of the system, that at some point it eventually samples so that we can monitor at least the state of the plants. So let's build this PTC infinite state traffic model. I'll skip through a bit of the algebra here. The main message is that first, the current state value is a function of the inter-event time and the previously sampled state. So psi of x being the state of the system starting from initial condition x at time kh is equal to some m, matrix m of k times x. And this matrix can be derived using standard linear systems algebra. The inter-event time is a function of the sampled state. So let's define kappa of x as the integer inter-event time, so inter-event time modulo h. So it's the minimum amongst the set of k's from 1 through k bar such that the triggering condition is satisfied, or in the worst case, k is equal to k bar. In this quadratic triggering condition, we can collapse the terms depending on k onto the matrix n of k. So we have x transpose and k times x bigger than 0. So our conditions are quadratic conditions on x and finitely many n of k's. This gives the following autonomous deterministic infinite state model. Xi plus 1 is equal to m of kappa of xi times xi, and yi is equal to kappa of xi. And because it's autonomous and deterministic, for a given initial condition, you have the full sequence of outputs predefined, essentially. So we can call ki of x0 as the ith output of the system when it starts at x0. And then we can properly define the minimum average intersample time, or MIST, of the system as the infimum amongst points in Rn of the limit average, or the limit inferior of the running average sequence. Now, this is the formula for MIST, but this is not a good formula to compute the metric because you have to find the infimum on an infinite unbounded set of a sequence for each of these points, which, by the way, is a sequence that is very slow to converge. So instead of using this formula, we use an approach based on abstractions. In a nutshell, what is our approach? First step is to obtain a finite state abstraction of our infinite state traffic model. So this traffic model is a concrete system. The finite state system will be called an abstraction. Second step is to solve a quantitative verification problem on the abstraction. That is, compute its infimum limit average. And this is easy to do for finite state systems. Step 3, we verify if the corresponding cycle that gives this limit average exists in the concrete system. And if it does, we can terminate. We will have found our limit average metric. Otherwise, we have to refine the abstraction and repeat. So on to the definitions. Let's define a weighted transition system and how to compute its limit average. A weighted transition system is a tuple x, x0, e, y, h, gamma, where x is a set of states, x0 subset of x is a set of initial states, e, a subset of x cross x is a set of edges or transitions. In our case, an autonomous system doesn't have actions, so this is a transition set. Y is the set of outputs, and h is the output map, mapping states to outputs. Gamma, finally, is the weight function mapping transitions to rational numbers. A run R, x0, x1, etc., an infinite run of S, gives a sequence of weights gamma of R, v0, v1, by just checking the weights of each of the transitions that happened. The value of the system is v of S, defined as the infimum amongst all limit average of all possible sequences of weights of the system. And limit average is defined in a similar way as we defined before. So onto the basic results. We rely on this theorem by Karp, where it's proven that we can compute the value of a finite state non-blocking system. It's proven that the value is obtained at some cycle of the graph defined by the system, and both the cycle and the value can be computed in polynomial time. A key simplifying observation in our case is that the weight of a transition, even in an infinite state model, is equal to the output of the outbound state. That means that the set of weight sequences is equal to the system's behavior. And thus, we have our first propositions that we can use simulation relations to have bounds on the value. So if SB simulates SA, then the value of SB, the abstraction, will be a lower bound to the value of SA, the concrete system. Now, obtaining exact values would be possible with a bisimulation. So if SA is bisimilar to SB, then we have that their values are the same. But bisimulations are rarely obtainable, particularly for PETC. And in fact, we don't really need a bisimulation. It suffices that the minimizing cycle, C, that we get using Karp's algorithm, exists in the concrete system. So with that, we defined a MACE simulation, a minimum average cycle equivalent simulation, which the name kind of says it all. Let SA and SB satisfy that SA is simulated by SB. Denote by MAC of SB the set of minimum average cycles of SB. If there is some behavior in SA of the type D, C omega, for some finite length sequence D and some C in the minimum average cycle set of SB, then SB is a minimum average cycle equivalent simulation of SA. That is, we have a simulation and one of these minimizing cycles happens to be a behavior of the concrete system after some transient behavior. This gives our first proposition is that if SB is a finite state simulation of SA, then the values are the same. So this Maze simulation is less strict than bisimulation. It's just a simulation with this additional requirement, but of course it's stricter than a simulation, so it's harder to get one. Well, this concludes essentially step 2. We have a way, if we have a finite state simulation, to solve a quantitative verification problem abstraction computing its infimal limit average. But now we have to be able to find an abstraction. So let's do that. For that, we use the approach of quotient models. Quotient models require a quotient state set, and a quotient state set is obtained by relating states which have the same output. So X is related to X prime if and only if their outputs are the same. And we build these quotient state sets by putting together all states with the same output. So QK is the set of all x's such that kappa of x is equal to k. And we have finitely many QKs because we have finitely many k's. And each of these sets is represented by a conjunction of quadratic inequalities by using the algebra that I showed before. So these quadratic inequalities are actually quadratic cones because we're comparing to 0 that start at the origin and go to infinity. So this would be a depiction of a case with 4 outputs of our quotient state partition of the state space. We can go further than abstracting based on the current output and actually abstract based on the next L outputs. This is called an L-complete quotient-based abstraction. In our case, we call this the L-complete PETC traffic model. Our system is XL, XL, EL, Y, HL, where the initial set is equal to the complete state set, and XL is a subset of all sequences of length L of outputs. And the state X is related to some sequence K1 through KL if and only if X belongs to QK1, the next state M of K1 times X belongs to QK2, so on and so forth. The transitions are based on what is called by Shimook and co-authors a domino rule, where a transition from X to X prime exists if the suffix of the X is equal to the prefix of X prime. This is natural to see because if my my next sequence of outputs is K1, K2 through KL, of course, my next state will have its sequence of outputs starting at K2, K3, so on to KL, and then another output that we don't know. So you place transitions based on that, and this example shows it. So for example, 222 has two states that start at 22, its suffix itself, and 221. So we place transitions like this. The output of the system, H of K1, K2 through KL is equal to the current output, the current sampling time again, K1. Look that this is essentially a refinement, right? The quotient-based partition would be only based on this set constraint here. While as we increase the samples, we are putting more and more constraints, but they're still quadratic constraints. So answering the question whether there exists a state related to K1 through K2 through KL is a question of checking whether there exists a point in the Euclidean space satisfying a conjunction of quadratic inequalities, which can be solved exactly using, for example, nonlinear SMT solvers. So using this framework of L-complete abstractions solves steps 1 and 3b. We have a way of abstracting and a way of refining. And this proposition summarizes how this refinement relation shows up. So let's see an example. With L equal to 1, we have this full graph here as the system, and the minimum average cycle is 1. With L equal to 2, we get rid of this cycle, 1 omega, and the minimum average cycle is now of value 1.5. Finally, with L equal to 3, we again break this cycle, and the minimum average cycle, 212 omega, has value 5/3. So the idea of abstracting using these L-complete abstractions is that if a cycle, for example, 1, 1, 1, 1, 1, 1 does not exist, then at some point, a sequence 1, 1, 1, 1, 1 for some value L will not exist as well. So eventually we break this cycle, and then the minimum average cycle will be different. So all we have to do now to be able to finish this algorithm is to verify if a corresponding cycle does exist. So to do that, we need some definitions. Let C equal to K1 through Km be a path in the abstraction, and C will typically be a cycle that is minimizing in the abstraction. We can define MC as the product of MKUM through MK1. So if the cycle K1 through Km exists, then if you apply this matrix MC to a sample, you have, again, a state that we should be giving the same cycle over and over again. Key observations. First, homogeneity is that x belonging to Qk implies that lambda of x also belongs to Qk for all lambda different than 0. These sets are quadratic cones, and as such, they contain rays. Another one is that if from some initial condition of the concrete system X, we have the cyclic behavior C omega, then X has to be related to an abstract state P, where P is the L-long prefix of C omega. Moreover, for any natural number K, MC to the power of K of X has also to be related to the same prefix, because its infinite behavior will be also C omega. That means that we can analyze the linear system x plus equal to mc times x. And in fact, all we need to do is to verify whether there is an invariant A of x plus equal to mcx that is a subset of QP. So let's illustrate how to do it. Take the simplest case, we have two different regions, two conic regions, Q1 and its complement Q2. These two are quadratic cones. And now remember, we have talking about linear systems, all their trajectories converge to or diverge from linear subspaces in general. And when I say in general, one sufficient condition is that the eigenvalues of the matrix MC have different magnitudes modulo complex conjugate pairs. So you can have a real eigenvector and trajectories converging to it, and for sure trajectories on it, or complex conjugate pairs of eigenvectors, and then you have trajectories spiraling in the plane supported by linear combinations of those vectors. But not only we have then that if a linear invariant belongs to Q, then we have a real trajectory. We also have somewhat the converse. If no linear invariant subspace belongs to Q, then all trajectories eventually leave QP. Being more precise, if no linear invariant subspace A of MC is such that A but the origin is a subset of the interior of QP, then all trajectories of this system eventually leave QP. With this, it means that all we have to do is to verify linear invariance. And to check these, we have a very simple result that it's a matter of getting the basis for the linear invariance, V, and checking whether V transpose QV is positive definite for a quadratic condition that is also positive definite. So with that, we can verify the finitely many linear invariants of a given matrix MC. This closes all the building blocks of our algorithm, but in fact, it is a semi-algorithm. And semi-algorithm because there are frequent cases where our procedure does not terminate. It will not terminate if one of the minimizing traces is aperiodic. And oscillatory but aperiodic trajectories modulo magnitude are very frequent even in linear discrete time systems. One example would be this one with alpha different than 0. The argument of the eigenvalues is the irrational angle arctangent of 2. And this angle is called irrational because it's not a rational multiple of pi. And this means that the states will never visit the same rate twice. They can spiral towards the origin, but they won't visit the same rate twice, which is very similar to a irrational rotation on the circle. In this case, the algorithm or the semi-algorithm would not terminate, but the gap can be estimated by calculating the maximal average cycle of the same strongly connected component that has the minimal average cycle. So on to a numerical example that will illustrate this a bit. We took a two-dimensional system with a triggering condition from Taboada, from the seminal work of Taboada, where we compare the Euclidean norm of the sampling error, the error between the current state and the sampled state. We compare this norm with a fraction of the norm of the current state. And if it's bigger, then we have to sample with trigger. For varying values of sigma, the larger sigma is, the less frequent you're expected to sample, and this is what we get by using this algorithm. We get almost a linear growth by increasing sigma optimized. The algorithm finished for all values 0.2 through 0.5, but it didn't for 0.1. We had to interrupt it before at L equal to 50, but the gap was estimated to be quite small. So this is one of these examples where we suspect that the minimizing behavior is aperiodic. CPU times were in the order of minutes. But then we moved on to a three-dimensional system, and then computation starts getting trickier. We use some parallel computation and improved the algorithm a bit, not totally, but we start getting CPU times on the order of an hour or so. Now, more interestingly, we checked for many different values of sigma, and for most of them, for a given example, the algorithm terminated, except for one, which by checking the eigenvalues of the matrices, we also suspect it to be an aperiodic case. With sigma equal to 0.1, it finished at the first iteration, didn't need any refinement because the cycle 1 omega actually exists. So the CPU time happened to be very, very small. Now, you can see that CPU times vary a lot. The most interesting thing here is that now we don't have that consistent increase in the MIST metric as you increase sigma. So it got stuck at 0.15 here, then stuck at 0.2 here, and suddenly a major jump to 0.475 at sigma equal to 0.9. So start seeing some unexpected behavior of the ETC. Well, this essentially is a conclusion to our work. So I think with this method to compute the ETC sampling for performance, I felt that we could free this elephant a bit, take it off the room. We presented this notion of maze simulation, which is quite straightforward, admittedly, but it's very useful for quantitative verification with mean payoff objectives. Computationally, our approach is still very challenging for ETC. Um, so this ties to our future work. Actually, our current work is mostly dedicated to using similar approaches for now mean payoff games to design better ETC strategies. And this is work that we just submitted to CDC, and it actually achieves remarkable results. Like our strategies get significantly better than the standalone ETC. Also, we were dedicated to further understanding ETC traffic behavior, understanding robust versus non-robust limit cycles, aperiodic versus periodic, chaotic patterns, so on and so forth. And we're almost done with that. And of course, towards practicality, we are interested in being able to tame computation and consider disturbances, noise, and things like that. Well, this concludes the presentation. I hope you enjoyed it. I'm looking forward to your questions. Enjoy the rest of the conference. Bye bye.